In this video, we're going to talk about an introduction to functions and evaluating them. Before we talk about what a function is, we need to talk about what a relation is. And so one definition of a relation is that it's a correspondence between two sets. So that's all fancy math talk for saying an input, like x, has a corresponding output, y. And three very popular ways to represent a relation are these three. So the first is a table. I am absolutely sure you've seen a lot of these XY tables or input-output tables that usually are represented with numbers that correspond to an output or each other. Another way is to take that table and graph it on the XY or Cartesian plane. Again, you've seen this a lot. A third, probably less popular way to represent a relation is through a map or a mapping diagram, which essentially is a lot like a table, except you use arrows to represent the relationship. All right, so now we can talk about what a function is. And one formal definition is a function from x to y is a relation, remember, correspondence between two sets, that associates with each element of x, which is again your input, one input for exactly one output. Not two, just one. And another way to talk about input, again, input and output have lots of names and different words that associate essentially the same idea. X, input, or domain. Domain might be a newer one to you. So when we talk about the domain, we talk about all of the x inputs, or the x values, in a function or in a relation. And the outputs also have many different names. So we know them as output values or y values, but we also call them the range. So a range of a function is all of its output values or y values. Now I don't know about you, but learning these two things, relations and functions, I start to think, are they the same thing? Are they different? Tell me. So the easiest way that I compare a relation versus a function is that every function is a relation, but not every relation is a function. So a function is like a fancy subset of a relation. So it's kind of like in middle school geometry where you learn that every square is a rectangle, but not every rectangle is a square. That's essentially the comparison between relations and functions. So let's take all that information and apply it to an example, or a bunch of examples, actually. So let's determine whether a couple of these relations represent a function. And double whammy, if they do represent a function, let's find its domain and range. All right, so what we're looking at as far as an example is called a map, where we have an input, or x values, or our domain, are calories of fast food sandwiches, and the output is grams of fat. Delightful. So I look at this and I look at the input versus the output, and I see this like teal-ish box as my input, and each number, 470, 670, etc., is different. Same with the output. That tells me that we have one output for each input. That's a function. The end. We happen to know that because we have one output for every input, and that's what defines a function. In our next example, we're going to compare and contrast two different maps. So in the first map on the left-hand side, we've got gas stations as our input and price of regular gas per gallon. And in the map on the right, we've got carats or gemstones and their output of their price. So upon cursory glance, these two maps look similar, but slightly different. They're similar to the first one where there are some straight across arrows, right? Like mobile goes to 271, 0.70 goes to $1,529. But we've got some arrows doing some different stuff. For example, both Shell and 7-Eleven cost $2.72 a gallon. And over on the right-hand side, we've got 0.71 going to both 1575 and 1952. And the difference, to me at least, is that this output comes from two different inputs, whereas this input goes to two different outputs. So it really depends on the arrow's direction. So we have to think about our definition of a function. And here's our handy dandy definition. And that tells us that each element of x, so each blue thing here, maps to exactly one element of y if it's to be a function. So each of these things has one arrow coming off of it. Sure, Shell and 7-Eleven share an output. That's okay in function land. So this one on the left is a function. But do I have the same thing on the right-hand side? I do not, because this input, this x, has exactly one element of y. Nope. This 0.71 goes to two different y's. So therefore, this one is a relation, but not a function. And in determining that the left one is a function, we have to figure out its domain and range. And just like in the first example, everything here, so Mobile, Shell, Sunoco, and 7-Eleven are in my domain, and all of these prices would be in my range. So in our next, technically 3 examples, we're going to be taking a look at sets. So sets are just another type of data set, to use the same word, that operate just like maps and function tables and graphs do. So let's determine if these 3 separate sets, so for example, that's a set, and that's a set, and they are a set of ordered pairs. So our 1, 4, that's x, y, x is 1, y is 4, etc. And what I'm going to do with those is turn them into a kind of table map hybrid. So what I do is I make a table of values, which you've done for many, many years at this point. So write 1 maps to 4, 2 maps to 5, 3 maps to 6, and 4 maps to 7. So normally as an ordered pair, like you would just leave it and then probably graph it or do something else with it. But because we're determining is this relation a function, I'm going to throw in some arrows and pretend it's a map as well as a table of values. So with these arrows, it's very clear, or at least it's very clear to me, that this thing is a function because every input is different and every output is different and it maps 1 to 1. So A is a function. And we would say that every x value, so 1, 2, 3, and 4, are part of the domain, and every y value, 4, 5, 6, and 7, are part of the range. So let's take a look at B and do the same thing. So here I have visualized in my table map hybrid thing, which is a little bit different than the table of values because the 4 would be written twice if it was just a table. So 1 maps to 4, 2 maps to 4, 3 maps to 5, and 6 maps to 10. The only real issue I see is with this 1 and 2 and this mapping to 4 thing. So if you remember back to our last example with the 2 maps, it's okay that this x1 and this x2, these 2 inputs, map to the same output. That's okay. It's if this 2 also map to 5. It's when you have multiple outputs per one input that you've got a problem. So B is also a function. And here is my lovely list map hybrid for part C, and everything was going great until this last ordered pair, which said, hey, -3 has 2 outputs, 9 and 8, which is fine for a relation, but not for a function, because in part B, it was a-okay for inputs 1 and 2 to have the same output. That's fine in function land. But what doesn't fly in function land is having one input that has 2 outputs. That don't work. So, unfortunately, C, not a function. Also just going to quickly throw in there that I totally forgot to find the domain and range of part B. So, just to say this really quickly, like we're at an auction, all of the domain is 1, 2, 3, and 6, which is the x values in the range is 4, 5, and 10. All right, goodbye. Just kidding, this is not goodbye. I'm sorry, you probably wanted it to be over, but it's not. So now, let's determine whether an equation is a function. So in this example, we're going to determine if the equation y equals 2x minus 5, which is an equation, you know that, defines y as a function of x. And you might be asking yourself, what does that even mean? So it's essentially asking the same question that we've been asking this whole video, which is this relation also a function? So you could make a table of values until you were blue in the face and determine that every x has one output y. You could make a map, same thing. You could graph it, which we're going to do in a second. But if you wanted to do this algebraically, which is another way, the first tip I will always tell you to do is get y by itself. One y by itself. And it's already in that format. So if you get y by itself and it equals something with x and maybe some numbers, you're good. That's a function. You only have a problem when you have like a y squared or y cubed or something else that's not just one y. So if you wanted to double confirm, you could graph it on Desmos or your calculator and see that, oh, there's one output for every one input. Cool, it's a function. Also, you know, a line is a function. So there are a lot of different ways to prove that y equals 2x minus 5 is a function. Or as we say in Mathland, it defines y as a function of x. So here's an example of an equation that we're not so clear on if that's a function or just a relation. So we've got x squared plus y squared equals 1. And if you know anything about functions or remember anything from your previous math education, you might say, ooh, that's a circle or an ellipse or something round, because x squared and y squared equaling a number usually makes a circular figure. So, is a circle a function? Let's find out. First thing I'm going to do here is graph it. So I graphed this thing on Desmos, and yeah, it's a circle. Cool. And so now my next thought is, well, are there two outputs for every one input? And it's not for every input, but if it happens at least once, where there is two outputs for only one input, meaning 2y for only one x, that's not going to work. That's not going to be a function. And so I tried 0.5. I plug that into the equation. I get 0.866 and negative 0.866. That's not a function. You can't have two outputs for the same one input. That's not going to work. So this thing is not a function. And just overall, a circle is not a function. It's a relation, but not a function. So that's how you would solve that graphically or with a table of values. Another way you could approach this to prove that x squared plus y squared equals 1 is not a function is by trying to solve for just that one y. Like what we did with that line example, I'm going to try to solve this for just one y. So the first thing that I do is subtract x squared, so I get y squared by itself, just so that we're all clear on the little symbols that I use. This like double slanted line just means apply the thing behind it, so subtract x squared from both sides. That's what that means. It saves space. If you want to use it, dope. If not, that's cool. So what I'm left with is y squared equals 1 minus x squared. I take the square root of both sides. Now, if you forgot, when you take the square root of a variable squared, so y squared, x squared, doesn't matter, you have to account for two different cases, a positive and negative case. That's different if it was just a number, like the square root of 4 is just positive 2, but the square root of a variable squared is positive and negative, whatever's on the other side of the equation. So that leaves me with two equations for y. That's not okay in function land, right? That's two different outputs for one input. That's not gonna work. So it's not a function. Also, cool little symbol notation. This like triple triangle thing means therefore. Feel free to use it. So yet another visualization of what a function is an input-output machine, which you may have seen before, where input is your x value or your domain, and your output is your y value or your range. Another way to think about this in more, I guess, scientific terms is that your x is your independent variable, like your x-axis, and your y-axis would be your dependent variable. So just putting that in there. So technically the second part of this video is about evaluating, which you actually have been doing in mathematics, but I wanted to talk about it in terms of a function. So let's just jump to an example. So let's say for the function f defined by f of x is equal to 2x squared minus 3x, which is our function, which is our rule. Let's evaluate these a through h parts. So I'm going to jump to my work. So for part A, which I'm sure you've done before, but to remind you, when we have f of 3, 3 is going to be my input or my x value. So every time I see an x, that's where I'm going to put 3. So 2 times 3 squared minus 3 times 3, and that ends up being 9. Part B asks you to do f of x plus f of 3. Well, we've already found f of 3, and that's 9. So f of x stays the same, so 2x squared minus 3x plus 9. Part C tells us to find 3 f of x, which means that I multiply f of x, so each of the terms, there are two terms, 2x squared and minus 3x, and multiply each of those by 3. So that means 3 times 2 becomes 6x squared, and 3 times negative 3 becomes negative 9x. So part D asks us to evaluate for negative x as my input. So all that means is to put negative x wherever there's an x in the original equation. So that becomes 2 times negative x squared minus 3 times negative x. So negative x squared turns positive, so that doesn't change. It's still positive 2x squared. And then this negative, that's the thing that becomes positive 3x. And part E is related to part D, except the negative stays on the outside. So all we're going to do is negate each term in the original equation. So that's like multiplying by negative 1 to each of the terms. So positive 2x squared becomes negative 2x squared, and negative 3x becomes positive 3x. Similarly to plugging in an x or a negative x, for f we plug in 3x. So wherever there's an x, that turns into 3x. So 2 times 3x all squared, so the 3x gets squared, minus 3 times 3x. So 3x squared is 9x squared, so 2 times 9x squared minus 9x. That's 18x squared minus 9x. Or if you want to be fancy and factor out a 9x, you can do that, and you're left with 2x squared minus 1. But leave the 9x on the outside. Part G asks us to plug in x plus 3, which is a little bit gnarlier. So I'm going to plug in x plus 3 every place that I see an x, so that becomes 2x plus 3 squared minus 3 times x plus 3. So the minus 3 times x plus 3, that's just distributing to negative 3 minus 9. Negative 3x minus 9, sorry. And this guy, don't just square the x and the 3 because you need FOIL. First outer, inner, last. Remember that? Yep, didn't go away. So combining all that stuff, distributing, yada, 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 I end up with 2x squared plus 9x plus 9. So our last example, I promise, is part H. And this whole thing, this f of x plus h minus f of x all over h, where h is not 0 because that would break the function, that's called the difference quotient. It comes up in calculus, if that's the route you want to take. But let's work it out in terms of what we have here. So the first thing that I do, the whole point of this is, my point is that I break this into pieces. So the first thing that I do is I plug in x plus h. So that x plus h goes in for wherever there's an x, so that gets squared and multiplied by 2, and that distributes the negative 3 to the x plus h on this part. So FOIL that guy. Combine all your like terms, which is 2x squared plus 4xh plus 2h squared minus 3x minus 3h. The point of the difference quotient is to have h's, not x's, but h's. I know that's weird. It's weird, but just go with me. And so the next part is to subtract your f of x. And f of x is 2x squared minus 3x, and when we subtract, it makes that a negative 2x squared and a positive 3x. So that cancels. So this negative 2x squared, bye-bye. This positive 3x, bye-bye. So I'm left with the 4x squared plus 2h squared minus 3h divided by h. And so when I get rid of all the h's and all those blue terms, I'm left with 4x plus 2h minus 3, which makes no sense right now, but it will one day in Calculus 1. And here's a little summary, which I'll let you read on your own if you care. If not, let's end this thing. All right, that's going to do it for this video. Thank you for watching.